Okay, before we do that though, let's just, we just sort of ran out of time at the end yesterday. So we were looking at an absolute value function. Let's just review very quickly just the concepts of how we dealt with this. So we had an absolute value function. If we wanted to build a table and sketch the curve to find out where the interesting places are, the way to deal with an absolute value function is to write it as a piecewise function, right? And we spent a little time doing that yesterday. And we ended up building a table. And I think I did something kind of dumb on this too. Did we need to, did we use the, I guess we're okay. I think I started to pick some test points here, right, to use the first derivative test. But do we really need to do that? Let's look at this. We know we've got an undefined first derivative at -3 and 2. We could use first derivative test, but we know that we've got positive concavity at -5. And then if we look on the other side of this place where the first derivative is undefined, so that's going to split up the second derivative into regions because the second derivative is undefined there too. If the first derivative is undefined, the second derivative is obviously undefined. So if we look at the 3 regions that are partitioned for the second derivative, we go positive to the left of -3, or negative second derivative in between -3 and 2, and positive to the right. So that's really all we need, isn't it? If we know that the function is continuous, and it is, right? The domain was all real numbers for this function, right? And we know that this is an undefined first derivative. All we need is the second derivative row to build this picture, right? Everybody agree with that? Yeah. Okay. No, it's not. I disagree with that statement I just made. How do we know? I thought about this for about 10 seconds after class yesterday, and I convinced myself I'd made a mistake by using the first derivative test, but now I think I didn't. How do we know that this could still be positive, a transition from negative to positive, and that wouldn't necessarily have to be a minimum? Right? I mean, we can reason that it has to be, but we could do this, couldn't we? It could actually just go like that too, right? And still be a sharp corner. See what I'm saying? Okay. So we have to verify that that's a minimum. We could finesse our way through this. Looking at the original function, can you tell me what the range of that function is? The range? It's always non-negative, right? Could be 0, but it can't be negative because it's an absolute value of a bunch of stuff. Absolute value, the output's always non-negative. So if we were just to look at that, like if we maybe included the range in our original function, that's one way we could convince ourselves that it has to do this, right? Those have to be minimums. Okay, everybody get that? The other way we could do it is we could just use the first derivative test, right? We could pick a test point. We know that if we pick a test point like,
5 again, is it test point?
say it again?
Like, use 5 again.
We could use -5. Right, so if we use -5 and we plug that into our first derivative, I'm not gonna go through the whole process of doing that, but if I were to plug that into my first derivative, what am I gonna find?
Negative.
It's negative, right? I'm gonna find it's negative there. If I plug in +5, I'm gonna find out that it's positive. And if I know that this is a horizontal tangent with a negative concavity, then I know that the function has to do this, right?
Yeah.
So without even picking a test point, I could fill in the sign of the derivative there as being positive, couldn't I? Right? Because I know if if this is a maximum, if it's a smooth maximum, it has to go from increasing to decreasing, right? And so that would be negative there. Everybody get that? Okay. And so then just by knowing those, if I know the sign's positive of the first derivative and the second derivative, it's gotta be increasing concave up, right? So there's some other ways I could do this, but once again, we could have really avoided that if we had just thought about the nature of this function. If the range is all non-negative numbers, then we knew what it had to do. Right. Okay. Questions on that? Okay. All right, so last one I want to look at is this guy. Just look at a trig function. Okay. So what's the domain of this? What are the domain of sine and cosine? No, just the domain of, the natural domain of a sine function. All reals, right? And cosine, same thing,
Yeah.
right? Okay, but all the other ones are not, are they? The other ones, and they're not because all of the other four trig functions have either a sine or a cosine in the denominator, right? Which is gonna give us some values where we're gonna get asymptotes, because we're gonna be asked to divide by 0. So what's in the denominator of cotangent? Sine is, right? Cosine over sine. So we know that cotangent x is undefined when sine x equals 0. So where's that going to be? If we look on the unit circle, where is sine 0? 0 and pi and 2 pi, it's just going to be at k pi, right, where k is any integer. Okay, so we know that x cannot equal k pi. Those are going to be all my asymptotes, right? And we probably, I mean, this is an infinite function. It's going to get kind of old to look at that. Well, we might restrict our answer to some smaller domain. We'll see. Okay, so what do we do? Take the derivative, okay? So we get y prime equals what? 2. What's the derivative of cotangent x? Negative cosecant. All you gotta do is remember what's the derivative of tangent is secant squared, right? So cotangent would be negative cosecant squared. Okay? Where is that going to be undefined? What's in the denominator of cosecant? Sine, right? So I get the same, that makes sense, right? I get the same places. The first derivative is undefined at the vertical asymptotes, which makes sense. Math gods are wise, right? They know it has to be undefined there. Okay, we got to find zeros though. Find our critical numbers. So how am I going to do that? Y prime is 0 where?
2 equals.
Cosecant squared, right? Okay, good. So when cosecant squared x equals 2, cosecant squared is just 1 over sine squared. So wouldn't that just be when sine squared x, if I just take the reciprocal of both sides, sine squared x equals 1/2? Okay? So keep going. If I square root it, okay. If I square root it, I'd get sine x equals, okay, almost. Plus or minus. Plus or minus 1 over the square root of 2, which is the same as square root of 2 over 2. Okay, so where does that happen? Where does sine equal positive or negative square root of 2 over 2? So sine is that's when the y coordinate, right, would be, so that's going to be at those two places right there, right, and at those two places right there, wouldn't it?
Yeah.
Okay, so I'm going to get all those places. Well, what are those places? Pi over 4. Okay, so what do those all have in common? Yeah, there's something else too.
Do the odd.
They're odd multiples, right? Odd multiples of pi fourths.
Yeah.
Okay, so then we could say that that's gonna be true. How do I say an odd number? Okay, yeah, how do I say an odd number? I say an even number, like if k is any integer, or let's use n, we already used k. So if n is any integer, how do I get an even integer? Well, 2n would be even, right? Does that make sense? Because if I double any integer, I'm getting an even integer. So to get an odd one, then I'm just going to offset that by 1. So I can either add 1 or subtract 1. So we'll do 2n, either one. We'll do 2n plus 1. That's an odd number over 4 times pi. Isn't that saying an odd multiple of pi fourths? Right? So those are all my critical numbers. Okay? We can start to make a table. How about if we limit ourselves here a little bit? Let's just go, what's our natural, or what's our restricted domain? So you guys probably talked about like a capital C cotangent or a capital, right? Where's the principal domain, I think is what we call it, principal domain of cotangent. It's gonna be, but where's the cotangent? It's gonna be a little less than that.
Is it 0 to pi?
It's gonna be 0 to pi. Yeah. Right. If we were to graph, let me show you what I mean by that. If we were going to graph cotangent, what's it look like? If this is the xy, yeah, it's gonna, and let's say we'll go by pi fourths. So there's pi fourths, pi halves, 3/4 pi, pi, negative pi fourths, negative pi halves, negative 3/4 pi, negative 2 pi. What's it look like? So we had asymptotes, we said, at all the multiples of pi, right? So I'm getting asymptotes here. Oh, why do I have 2? I don't need a 2 pi over there, do I?
Yeah.
And this is just gonna keep repeating, right? It's cyclical. So then if we use the unit circle to guide us here, I'm telling you, the unit circle is, it's everything you need to know is on that unit circle. Okay, so where is cotangent equal to 0? It's going to equal to 0 in the numerator, which is cosine is equal to 0, right? Cosine equals 0 here and here. So at the odd multiples of pi halves, so it's going to go through pi halves, it would go through 3/2 pi, it's going to go through negative pi halves. Okay, so where is it going to be positive and where is it going to be negative? It's cosine over sine. So it's going to be positive where they're both positive, right? So where is it positive then? 0 to pi over 2, right?
Yeah.
Okay, so we know it's going to be positive here, and it's going to be negative in quadrant 1. Agreed?
Yes.
Okay, so then isn't it doing this? Right? It's going to be positive in quadrant 3 because they're both negative. Everybody agree?
Yes.
So if it's positive in quadrant 3, that's going to be right here, and negative in quadrant 4, right? If I back up, if I use negative angles, it's negative in quadrant 4, right? So it's gonna be negative here, and it's gonna be positive in quadrant 3, which means I have to back up
Yeah.
angles between negative pi halves and negative pi, right? So it's gonna, it follows, my point is it just follows that same pattern over and over and over again,
Uh-huh.
right? So then when we define the principal domain of a trig function, which one are we gonna pick?
Zero.
0 to pi, right? And let's think about why is it, and I'm just throwing in some trig with you, any chance I get, I'm throwing in a trig with you. So why do we pick a principal domain? Because it repeats, but there's another reason. Another important reason that we pick only, so I'm gonna make the principal domain, let's make that a different color. So that's gonna be bright yellow. There you go, yeah, how about that? So how come I pick a principal domain instead of the entire domain? What do we do a lot with trig
Well, you
functions?
can just add, by back, or like, you can add K, or.
You can, that's
like,
right, I mean,
So if you have all of these numbers, you can just add the even or odd multiples that are.
right, the other ones would be pretty predictable, wouldn't they? Right. Okay, but there's another reason for this. If you think about the kinds of things you do with trig functions, a lot of times we're inputting angles and solving for numbers, but sometimes we're trying to solve for angles, right? Like what if I'll give you an example. What if I had something like this? What if I had the sine of x equals 0.3? What would I do?
You do arc
I
sine.
have to do arc sine, right? Or if that were a cotangent, I'd have to do arc cotangent, right? So I have to use the inverse functions a lot of times to solve trig equations, right? Okay, well, if I want to use the inverse relations, I would prefer that those were inverse functions, right? And so what's it mean for a graph to have an inverse function, right? If I take the entire cotangent graph and I invert that, right? Think what that does to the graph. Well, we had a trick for this, right? If I want to come up with the graph of an inverse relation, do you remember the trick I showed you? Rotate it 90 degrees counterclockwise, and then flip it over, reflect it over the y-axis. So you can see what this is going to do. We're going to get these repetitive cycles, but they're going to stack up vertically and they violate the vertical line test, right? So it's not a one-to-one function if I take the entire relation, is it? Right? Here it's, what is this? This is a many-to-one solution. I can take many different inputs and get the same output with my cotangent function if I take the entire domain. Everybody get that? Like there's an infinite number of places on my cotangent graph where y has that value, right? So I can input many x values and get back one y value. But the problem is if I invert a many-to-one relation, I get a one-to-many relation, right? If I invert this thing, aren't I going to get something like this? And you get the idea, it's going to be, right? And so now I could input one x value, and I'm going to get, oh, what did I just do that? I have no idea what I just did there. So if I input one x value, I'm going to get an infinite number of y values, so it's not a function, right? So the way we fix that is we're only going to choose one cycle of this relation, and then it's one-to-one, and it acts like an inverse. I have an inverse function there, right? So just a quick reminder. You'll see that stuff again in college, but just a quick reminder why we do this. So here's our, what if we just take this thing, just to make things a little bit easier, let's just take this function on its principal domain only, from 0 to pi, when we make our table. Okay? So we've got our domain greater than 0, less than pi, right? We found that we had, on that domain, we had critical numbers at pi fourths, 3/4 pi, 5/4 pi, 7/4 pi.
But just five.
Oh, yeah, pi fourths and 3/4 pi, 'cause we're only doing that, you're right, whoops, so we go. Pi fourths, 3/4 pi, and those were zeros of my first derivative. What was kind of interesting about pi halves, if we looked at our graph? What's the value of the function at pi halves, you told me?
0.
0. Okay, so we could include that, couldn't we? So there's an ordered pair that's convenient, right? Oh, but was that 0 for our, wasn't for our function though,
No.
not for our function. That was just for cotangent, so I gotta get rid of that. Okay. What else? Gotta keep going. Okay, so we got everything we needed to out of the first derivative. Thank you. What about second derivative?
We need to do it.
So we can do the second derivative. Now, to do the second derivative, what is cosecant squared x?
Cosine x times cosine.
Okay, cosecant x times cosecant x, so it'd be the quantity cosecant x squared. That's our shorthand. Remember, that's actually the outside function when we do chain rule here, right? So y double prime, derivative of 2 is 0, but then I'm going to get
Negative.
derivative of hand squared is 2 hand, right?
Yeah.
So I get 2 times -1, so I get -2 times hand, which is cosecant x, times the derivative of hand. What's the derivative of cosecant? Cosecant cotangent, right? So then if we simplify this, negative times negative is positive, and I'm gonna get +2 cosecant squared cotangent,
Yep.
right? Okay, but I can never, I don't know about you guys, but I don't think in terms of cosecants and cotangents. I think in terms of sines and cosines,
Yeah.
right? So why not split this up into sines and cosines? Cosecant is 1 over sine, right? Cotangent is cosine over sine. So I could write that as 2 cosine x over sine cubed x, right? I got a sine squared times a sine. Okay? So there's our second derivative. Unsurprisingly, where is it? Okay, so where is the second derivative equal to 0?
2 cosines.
Okay, so when cosine is 0, the second derivative is 0, right? Okay. And on our unit circle, that's just gonna be at pi halves, right? Between 0 and pi, that's the only place. It's gonna be undefined when sine is 0, which
0.
unsurprisingly, right, that's what I meant, so that's gonna be at 0 and pi. Why? Well, because the functions of it, I have asymptotes there, right, so you can't define a second derivative where you have an asymptote. Okay? And we don't even need, I won't even write that part, I guess I will. But. Okay, so if we add this stuff to our table then, we had pi halves, we had a 0
Yeah.
second derivative, okay? So this is a pretty easy table to deal with. Then. What do I have to do to really figure out what's going on?
You need
Calculate y
pi
over pi.
plus
Okay, calculate what?
Second derivative.
Second derivative at my first derivative critical numbers. We'll use the second derivative test. And that's gonna give us 2 birds with 1 stone, right? I'm gonna figure out what's the nature of these first derivative critical numbers, but it also is gonna tell me whether that's an inflection point, right? Okay, so if we evaluate just the sign of the second derivative, here I've got it in nice factored form. If I'm gonna evaluate this at pi 4ths and 3/4 pi, right?
Yeah.
Yeah.
Okay, so if we do that's supposed to be a 4. What are we gonna get here? In quadrant 1, I'm getting positive over positive, all right?
Yeah.
So that's positive. What about quadrant 2? If I do f double prime of 3/4 pi, in quadrant 2, sine is
That's the positive.
positive, cosine is
Negative.
negative, so I'm getting negative over positive is negative. So what is that? That's an inflection point, isn't it? Yeah. Okay, what about these guys? What are these guys? 0 first derivative tells me
Horizontal.
horizontal tangent. Positive second derivative, concave up, right? Over here I've got horizontal tangent, concave down. And then what's this gonna look like? I'm going from, we could connect these things together, couldn't we? So I'm going from increasing to increasing through a non-horizontal inflection point. Right, so it's not a horizontal line, it's just gonna have to look like that, isn't it? See what I'm saying? Okay, and that tells us everything we need to know. We could ascertain the limits here without even doing any work. What's gonna be the limit as x approaches 0 from the right? It's gotta be infinity, doesn't it? Because look, we've got a minimum with nothing in between, no other critical numbers in between pi 4ths and 0. So we know that's gotta be infinity. And what's the limit of, as we approach pi? Well, it's gotta be negative infinity. And we could've just taken the limit if we wanted to, right, up here, but we don't need to. Okay, and then that gives us our picture, doesn't it? So we get something like, I'm not gonna put the points in, but we could evaluate the function at these points and get concrete numbers to put in, to anchor it on the graph. But we're getting a minimum here, okay? Somebody do this, let's just get a number. Plug in pi 4ths. Cotangent of pi 4ths is 1, so we can do this pretty easily. Pi 4th, that's 1. 2 times pi 4ths is pi halves. So pi halves plus 1 is like 2 point, what is that gonna be like? 2.6-ish, 2.5 something. You get an idea, right? So it's positive, not too big. Something like that. So here's a point. At 3/4 pi, what are we gonna get? Cotangent's gonna be -1. And so I'm gonna get 2 times 3/4, I'm gonna get 3 halves pi minus 1, so what's that? Like, 4, is that gonna be like 4.7-ish,
4.7.
yeah.
But you have to subtract the
Say it again.
Never mind.
Didn't I subtract it? Oh, no, it should be 3.17, right? So it's gonna be just a little bit higher, so up here somewhere. And that's probably all we need. Now we should be able to connect this thing. I know it's going like this. There's my inflection point. Oops, hang on. Did I do that right? Oh, yeah, I put down. Now it's turning to, so it does something like that. And then I get asymptotes That make sense? Okay. All right. I think we're good. We hit about everything we can hit.
Are we still bringing patio tomorrow?
Oh, we probably should do a little something for Pi Day, shouldn't we?
We should do a